one problem. Here it is the 21st. The emissive power of a sphere. Let us read that one. The emissive power of a sphere of area 0.02 meter square is 0.5 kilocalorie per second per meter square. And what is the amount of heat radiated by the spherical surface in 20 seconds? So amount of energy which is radiated, that we need to calculate. Let us calculate that one. So before that one, what it is given? The area 0.02 meter square. What about the we say question mark? We are need to calculate that what? Q. We need to calculate the amount of means radiation it will take place within a second, that is 20 seconds, means time it is also given. And here it is, the one more thing it is given, that is E, and we need to calculate the value of Q. So let us calculate that one. Let us calculate this Q. So Q question mark, before that one 21, Q is equal to how much? And E it is given. What it is given, that we need to write. Here it is E 0.5 kilocalorie per second per meter square. Kilocalorie per second meter square. Now what about the time? Time it is given, that is 20 seconds. What about the remaining term which is also given? Here EA and area is also given. How much is the area which is given here? It is area is 0.02 meter square. 0.02 meter square. So we know very well that E is equal to Q upon AT. This is the basic formula we know very well. This is the formula. Using this one, we are going to need to calculate the Q. So Q is equal to E into A into small t. So Q is equal to E, that is 0.5 into area, that is 0.02 into what about the time? It is 20 seconds. So if I am going to shift the point 5 into 10 raised to power minus 1, I can write this. So what about this? I can write this as a 2 into 10 raised to power minus 2, or I am also going to write this 2 into 10 raised to power 1. So go on collecting the power. Minus 3 plus 1. That is, we say that this get cancelled. Only remaining factor is 5 by 2. Means 5 into 2, 10. 10 into 2, 20. So accordingly, I am going to get the answer. The answer is 0.2. How? That we are going to get. Let us get this Q. 5 into 2, 10. 10 into 2, 20. 20 into 10 raised to power minus 2. Shift the point by 2. So required answer it is 0.20 kilocalorie. This is about the final answer regarding 21. Now we have the problem number 22. Let us start with this one. Compare the rates of emission of a heat. Compare. See, the comparison means there is no unit of answer. Okay. Compare the rate of emission of a heat by a black body maintained at 727 degrees Celsius and at 227 degrees Celsius. If the black bodies are surrounded by enclosure, that is means of black, at 27 degrees Celsius, means a black body, it is enclosed at 27 degrees Celsius. What would be the ratio of their rates of loss of heat? See, rate of loss of heat. We only know that loss of heat means a Q, but rate of loss of heat means with respect to time. So we need to get that. Initially the temperature of surrounding is how much? That is the important. The temperature of the surrounding that we are going to write, or we are going to write the data regarding the 22. Here it is 22. So here the temperature of the surrounding, let us consider the outer temperature. It is given by 27 degrees Celsius, means 27 plus 2, 73, that means 300 Kelvin. What about the temperature of the body initially? At different temperature it is kept. Initially it is at 727 degrees Celsius, that means 727 plus 273, that means it is 1000 Kelvin. What about the temperature T2? It is given by how much? Second temperature it is 227 degrees Celsius, that means 227 plus 273, that gives us a 500 Kelvin. So accordingly, we have the basic relation, that is basic formula I am going to write. According to Stephen's law, we know very well, according to Stephen's law, with respect to surrounding, one, already we have taken this formula. We know that E is nothing but emissive power, that is dq upon dt, and which is given by sigma into A into T raised to power 4 minus T0 raised to power 4. What about this? This is the temperature of the body, this is temperature of the surrounding. This we have already taken in the previous video in case of Stephen's law. But before that one, you will have to observe the relation which is given in that video and start solving this. So let us see this one, how we need to solve that. Let us consider the event with reference to this basic formula. I am going to substitute all the values. This is for the black body. For black body. If it is not the black body, if it is ordinary body, then I need to multiply it by E. But this is a black body. So discarding E or substituting E is equal to 1. So here sigma is a constant, that is known as constant of proportionality, and whose value is, how much is the value which is given? I not written there, but here don't need to write that because we are going to take the ratio and sigma is a constant, it is get cancelled. And the body is same but kept at a different temperature. So I need to substitute all that. Here it is sigma into A into, here instead of that one, T1 raised to power 4 minus T0 raised to power 4. I need to substitute all. Here it is even is equal to sigma into A into T1 is how much? 1000. Here it is. I'm going to write in a square bracket instead of a rounded bracket so that I can easily substitute 1000 raised to power 4 in the bracket. So what about the surrounding temperature? It is 300 raised to power 4. This is equation number 1. What about the E2? If E2 it is taken sigma into A into, what about the second one? That is 500. Okay, that is T2. Okay, two equations for the E2. I'm going to write here equation sigma into A into T2 raised to power 4 minus T0 raised to power 4. Going to substitute that, raised to power 4 minus 300 as it is, because 3 means 300 means the T0, which is a constant surrounding temperature. So this is equation number 2. Let us take the ratio of these two so that these terms get automatically cancelled. Only the remaining factor it is even upon E2. So here it is 1000 raised to power 4 in square bracket into 300 raised to power 4 upon, what about this? It is in square bracket 500 raised to power 4 minus 300 raised to power 4. Now after this step I am going to solve here. I will continue that one. Even upon E2 is equal to, here it is 1000 I can write as a, we say 10 raised to power 12. How? Because here 10 raised to power 3 raised to power 4 4 3s are 12. So it is 10 raised to power 12 minus, here it is 3. 3 into 10 raised to power, how much? It is 2 raised to power, we say it is 4. What about this one more step I am going to increase? Here it is 5. 5 into 10 raised to power 2 raised to power 4 minus 3 into 10 raised to power 2 raised to power 4. Here it is 3. I can 300. I can write 3 into 10 raised to power 2. As it is raised to power 4, I am going to substitute. What about this? I can write this as a we say 10,000 into 10 raised to power 8, because 10 raised to power 4 I am going to write here, minus 3 into 10 raised to power 8. So here it is similar power, 5 into 10 raised to power 8, and what about this 3 into 10 raised to power 8? This is taken in bracket. So that clear understanding we have, this is minus. Okay. So after solving this, I am going to write 10,000 minus 3. 10,000 minus, not the 3, because here it is raised to power 3. Means 3 into 3 into 3 into 3. How much? 81 it is. 81 into 10 raised to power 8. So 5 minus 3, not the 3. Here it is 5 not. It is not the 5. 5 into 5 into 5 into 5. Means 5 into 5, 25, 25 into 25, 6, 25, 6, 25. Minus, once again the 81 into 10 raised to power 8. 10 raised to power 8, 10 raised to power 8 get cancelled. After solving this, I am going to get the answer, that is 18.23. And as it is the ratio of similar quantity, that is even upon E2, this value even upon E2 is equal to no unit. Okay, it doesn't possesses any unit. So answer is 18.23. Let us start with the problem number 23. I am going to read that one. Pay concentration on that one. Earth's mean temperature can be assumed to be 280 Kelvin. How will the curve of blackbody radiation look like for this temperature? Question mark. Find out, we say that find out the maximum wavelength in which the electromagnetic spectrum, the particle of electromagnetic spectrum, does this value lie? We need to calculate that value, and we are about to give the we say region, and in which region it is going to be get that wavelength. Let us calculate this. So one by one I am going to write what exactly the given factors for the 23. So the temperature it is given, that is 280 Kelvin directly, no need to convert anything, and we know that B value, that is 2 point, we say it is given constant, means constant we say, and its factor it is given 2.897. 2.897 into 10 raised to power minus 3 meter Kelvin. Okay, this is meter and this is Kelvin. So we need to calculate the maximum wavelength and draw the conclusion on the basis of that one. So according to Wien's displacement law, I am going to write the equation, that is lambda max is equal to, or it is inversely proportional to absolute temperature, but there is some constant known as Wien's constant, and which is given by B by T. B value it is known, T value it is known. So let us calculate that value, that is lambda max is equal to, substituting 2.897 into 10 raised to power minus 3 divided by 280. If we solve this, we are about to get the answer, that is 0.01035 into 10 raised to power minus 3 as it is. This is the answer of this ratio. After getting this one, I am going to express. Here it is 1, 2 means 1.035 into 10 raised to power obviously minus 5. That is in meter maximum. So this is our expected answer. But what about this wavelength? This wavelength is related to the microwave region. So this wavelength are related to which region? Microwave region. There are certain regions that we are going to take in NEET CET JEE concept, but here it is. This concerning wavelength, it is related to the microwave region. This is the conclusion that I am going to draw. Okay, this is the wavelength which is true one, and this is found exactly, that is, it is in the microwave region. So accordingly, this lies in the microwave region. That means obviously it is in the form of, we say, particles of electromagnetic waves. Obviously it is energy which is radiated in this region, that is microwave region, and obviously it does not lying it, means it is correct one. That means this wavelength concerning to this one, it is related to the microwave region. Now let us start with the problem number 24. Here it is the problem before you. A small blackened solid copper sphere of radius 2.5 centimeter is placed in an evacuated chamber. The temperature of the chamber is maintained at 100 degrees Celsius. At what rate energy must be supplied to the copper? See, at what rate? At what rate means obviously Q is just the radiation, but Q upon T or dQ upon dt is nothing but a rate of radiation or energy must be supplied to the copper sphere to maintain its temperature at 110 degrees Celsius. Means obviously surrounding temperature it is given 100 and we'll have to keep the body at 110 degrees Celsius. So take Stephen's constant, that is 5.76 into 10 raised to power minus 8 joule per second meter square Kelvin raised to power 4. And treat sphere as a black body. Obviously it is black body, means E is equal to 0. E is equal to 1. E is equal to 1. Let us start with the 24. Here it is. The surrounding temperature it is given, that is T0. It is equal to 100 degree Celsius. That means 100 plus 273. That means here it is 373 Kelvin. What about the T temperature of the body? 110 degree Celsius. That means 110 plus 273. It is, we say that it is 383 Kelvin. So what about the next value which is given? Here the radius it is given. Radius is how much? 2.5 centimeter. Means obviously 2.5 into 10 raised to power minus 2, we say that it is in meter. So we need to calculate the area first, and then we need to get this dq upon dt. But we know that dq upon dt formula, we know dq upon dt is equal to A into sigma into A into T raised to power 4 minus surrounding temperature raised to power 4. But here for the, we say that black body seems to be considering sphere as a black body, E is equal to 1. So what about the area? So after substituting all the factors, if we need to get the area, we can calculate the area separately. We can also insert this one, and we know that sigma value, before starting this, we are going to write the sigma value, that is 5 point, write it in a briefly, sigma 5.67 into 10 raised to power minus 8. What about the factors or unit it is given? Joule per second meter square raised to power means meter square into Kelvin raised to power 4. This is the given factor. What about the sigma? I'm going to substitute now. 5.67 into 10 raised to power minus 8. What about the area? It is 4 pi r square. So separately I'm going to substitute this value. Here it is t raised to power 4 means 100 means whatever the answer it is 3. I'm going to write it in a square bracket so that easily understand this one. 383 raised to power 4 minus 373 raised to power 4. What about the area? Area is equal to 4 pi r square. 4 into 3.14 into now 142 into or 14 we can say that r square. R square means here 6.25 square of 2.5 6.25 into 10 raised to power minus 4 squaring. After solving this we are about to get the answer. See, here it is 4 into 3.142 into means what is the multiplication we are going to take. After getting this, our answer comes out to be for the area it is 7.855 into 10 raised to power. See this one. After multiplying 4 into 3.142 into 6.25. The answer comes out to be 10 raised to power. Here 7.855 into 10 raised to power minus 3 meter square. This is the answer for the A. And we need to substitute that into this. That is dq upon dt is equal to 5.67 into 10 raised to power minus 8 into 7.855 into 10 raised to power minus 3. What about the bracketed term? Here it is 383 raised to power 4 minus 373 raised to power 4. Hence, after solving all these, we are about to get the answer, that is dq upon dt is equal to, after solving means 5.67 into 10 raised to power minus 8, once again 7.85, 5 into 10 raised to power minus 3, and after getting the power 4, a minus power of that one into square bracket, and after solving that, we are about to get the answer, that is 0.962, that is watt. Obviously, it is energy. Okay. Let us start the last problem, that is problem number 25. Let us read that one. Find the temperature of a black body if the spectrum has a peak at, we say lambda max is equal to 700 nanometers. That is visible light, visible spectrum of light. B, that is lambda max is equal to 3 centimeter. It lies in the microwave region. And C, lambda max is equal to 3 meter, which is FM wave. Okay. Take the Wien's constant is a 2.897 into 10 raised to power minus 3 meter Kelvin. So let us calculate the temperatures at that regions. See, let us start. Here it is 25. What exactly it is given? At 3 steps, I am going to write that. Before that one, B value 2.8 or 2.897, that is B value, into 10 raised to power minus 3 meter Kelvin, which is given. What about the different wavelength which is given? Lambda max 700 nanometer. Lambda max 1 we say 700 nanometer means 700 into 10 raised to power minus 9, or I am going to write that 7 into 10 raised to power minus 7 meter. Okay, this is lambda max 1. Okay, this is the value which is given. What about the lambda max 2? Which is that region? That also going to write that it is a visible region. Actually, it is visible, and this is a microwave region, that is 3 centimeter. 3 centimeter means 3 into 10 raised to power minus 2, that is we say microwave region. microwave region of wavelength. And what about the lambda max 3? It is, we say that it is 3 meter, which is given. How much? It is 3 meter. Let us see. Yes, it is 3 meter, means FM radio. FM radio region. So for that one, the first step I need to calculate the temperature concerning to that first. That is T1 is equal to B upon, or vice versa. It is lambda, because basic equation, that is lambda max is equal to B upon T, according to which law? Wind displacement law. This is a max one. Obviously this is a modified equation. So concerning to that one, what about the temperature? Here it is, B value 2.897 into 10 raised to power minus 3 upon lambda max 1, that is 7 into 10 raised to power minus 7. After solving this, I am about to get the answer 4138 Kelvin for the first. Now for the second, that is in the microwave region, the similar we are going to substitute, that is B upon lambda max 2. What about that? Here it is the 2.897 B value as it is, that is into 10 raised to power minus 3 divided by this one. What about this one? 3 into 10 raised to power, here it is minus 2. So the answer comes out to be, after solving this, 0.0966, that is, we say temperature in Kelvin. So let us check out. Yes, this is the answer. And later on, the third one that I am going to substitute, I am going to get the answer, that is T3 for the FM region, B upon lambda max 3. So going to be substitute. What about that one? 2.897 into 10 raised to power minus 3 upon, what about the next region? Already we have taken this. What about this? This is 3 meter. So divided by 3. If we need to solve this one, the answer comes out to be 0.966 into 10 raised to power minus 3. Because if we cancel this one, we are about to get this value, and as it is 10 raised to power minus 3 in Kelvin. This is related to the temperature, and these are the answers before you for the T1, T2 and T3. Thank you.